Hello and welcome to this video. So this video is part of the class Introduction to Artificial Intelligence and Machine Learning for Engineers. So today what we are going to talk about in this lecture is logistic regression. So as a reminder, we said that there is two main class of machine learning, or maybe three main class depending on how you classify this. So the first thing, and that's the thing that we have been talking about so far, is supervised machine learning. And then you have unsupervised machine learning. So we talk about supervised machine learning when you have a given input and you want to predict a given output. So you have a given X, you want to predict a given Y. So the data have some label Y. On the other hand, when you do unsupervised machine learning, then there is no label. You only have some input X, and you want to find some patterns, some clusters within those data. And then there is a last type of machine learning, which is reinforced machine learning, where in this case you learn based on the feedback of your environment. So far what we have been talking about is solely supervised machine learning, and we have been talking about different algorithms to do some regression problems. So we talked about linear regression, we talked about lasso, we talked about artificial neural network. Those are all regression algorithm, in the sense that you have a given feature X and you want to predict the label Y. So you want to develop a model that will predict the given value for the label Y. And in this case, in the case of regression, the specificity of regression is that Y can be a continuous function. So for example, Y can be a real number or several real numbers that can continuously change. The value can continuously change. So now what we are going to talk about in this lecture is another type of supervised machine learning, which is now classification. And the main difference between classification and regression, those are both supervised machine learning algorithms. So your goal is still to predict a given label Y, but this time Y is going to be can only take discrete values. So in this case, the label Y can only be equal to 1, 2, 3, or 0 and 1, but it cannot be like a continuously changing, like 0, 1, 0, 0, 1, 0, 2, 0, 3, etc. In this case, you have a discrete number, so you have a finite number of possibilities for Y. Those are going to be different classes of data. In this case, you want to predict for a given set of input which class do those data belong to. So we're going to see some example about to explain what this means, but here the main difference is that we are going to predict as a function of some inputs, as a function of some features, we're going to predict if not a given output that can continuously change, but a given output that can only take a few selected values. So let's see some example of classification problems and how they differ from regression problem. So a first example, that we are facing in our everyday life is, for a given email, is it going to be a spam email or a non-spam email? So that's something that we are facing pretty daily in our mailbox, is that our mailbox or our mail service needs, for each email, based on certain features that describe this email, based on the types of keywords, based on the size of this email, etc., it needs to predict whether this email is spam or not spam. So in this case, the label Y would be, for example, 1 if the email is spam, and would be 0 if the email is not spam. And in this case, there is nothing in between spam and not spam. Either the email is spam, either it's not spam, and there is nothing in between. between. So in this case, that's an example of classification because you have only two different classes of email, the spam email and the non-spam email. And your goal in this case will be based on certain features describing this email to predict whether it's a spam email or a non-spam email, to predict which class does this email belong to. Another example is sickness test. So if you have a given test that is aiming to predict whether a given patient has a given malady or a given sickness or not, then in this case you have only two possible outcomes for a given patient. Either the patient is sick, so it has the sickness that the test is aiming to predict, or it is not sick. So there is only two classes, there is nothing in between. So same thing, sick would be y equal 1, not sick would be y equals 0. And in this case, the goal is based on certain features, some certain characteristics of the test, you want to predict whether the patient is going to be sick or not sick. So that's an example of classification problem. Some other examples that are a bit closer to civil engineering. For example, if you have a given structure, you want to predict based on certain types of sensor signal, is this structure damaged or not damaged? So that's an example of classification problem, like there is only two classes, damage or not damage. Other examples for a given soil you want to predict is if it's going to liquefy. Is there any risk of liquefaction or no liquefaction, based on the different features, like for example the amount of water or the characteristics of the soil, etc., etc. Or a last example would be if you have a given cement, there is different types of cement. There is a cement type 1, there is a cement type 2, there is a cement type 3, etc. So you have different types of cement, and if your goal is to predict for a given cement based on certain features which type of cement it is, then that's also a classification problem. In this case, it's a multi-class classification problem because it's not a binary classification. Here so far, email, the sickness test, the structure, or the soil. This was a binary classification because there is only two classes. Either it is spam or not classification. Okay, so either it is spam or not spam. There is only two possible classes. But in the case of cement, there is at least three possible classes for cement, maybe more. So in this case, it's going to be not a binary classification, but a multi-class classification, because in this case, the number of possible classes that you need to choose from is more than just two. So let's see a first example of classification problem and how a classification algorithm like logistic regression would work. The first thing to say is that despite the name of logistic regression of course sounds like regression, but that's actually a classification algorithm. It's actually going to be used for classification problem. It's going to be used to predict for a given set of features what will be the corresponding class. So let's see an example on how this can be applied. So for example, let's consider that you have a given structure and you want to predict whether this structure is going to break or not. Is this structure going to fail, or is it not going to fail? So that's the y-axis, that's the label, that's what you want to predict. Either y equal 1, and it means that the structure is going to break. And on the other hand, if y equals 0, then it means that the structure does not break. So this is what you want to predict. This is the label. And then the information that you are going to use to make this prediction are the features. So this is the same as in a regression problem. You want to predict a given label for a given observation. This is the outcome. This is the output. This is what you want to predict. And to predict this, you are going to use certain features. The features are the information that you have access to, and you're going to use the knowledge of those features to make your prediction. So this is going to be the inputs of the models. You can have one input or more than one input, several features. So here we're going to take an example where you have only one single feature, which is the load that you apply. You apply a given load to the structure, and you want to predict whether this structure is going to break or not. So that's a classification problem. You have one feature, which is the applied load, and you have two possible classes of structure, the structure that are going to break for this given load, and the structure that are not going to break. So you have two possible classes, two possible outcomes. So then, since it's supervised machine learning, the first thing that you will need is some examples. So you need some observation of some training example that you are going to use to train the model. So you need to come up with some data, make some observation, make some measurements that you are going to use as a training set for the model. So here in this case, you are going to do different measurements. You are going to apply different types of load, and sometimes the structure is not going to break, and then you are going to continue to apply some other values of loads, and sometimes the structure is going to break. So those are going to be the training example. Those are the observation. The observation here can either be 0, 1, the structure breaks, or it doesn't break. There is no other possible outcome. So if you face these types of problem, then your goal is, based on those training data, to train a model that can be used to predict whether a given structure is going to break or not for a given load. To try to understand, based on this load, is the structure going to break or not? So a first possible ideas for this would be to say, well, I'm going to use simply a linear regression. I'm going to just fit those data here by a linear model like this. So in this case, that's what you would get. You would get a linear model like this. In this case, it means that the hypothesis of your model would be the same as for a linear model, which is that you have some coefficient theta, you take the transpose of theta, and you do a matrix multiplication by x. For example, in the case when you have only one features for linear regression, then your hypothesis is theta naught plus theta 1 times x. That gives you a linear hypothesis, a linear model. The problem with this is that you could say, I'm going to use this model, and I'm going to say, if this model is larger than 0.5, I'm going to say that I'm going to predict that for this feature, the structure is going to break. For this value of the applied load, the structure is going to break. Or I'm going to say that if the model becomes lower than 0.5, if the hypothesis becomes lower than 0.5, then I'm going to predict that the structure is not going to break, that the structure is going to maintain its integrity. So in this case, that would work pretty well, but there is a drawback with this, is that if you add the points here at very high applied load, and so obviously the structure is going to break. Now if you try to fit a linear model based on this, because you have this point here, your linear model will be very affected by this point over there, and when you will try to minimize the mean square error, then your model will become like this. And if your model becomes like this, again, you are going to say that I'm going to check when is the model becoming larger than 0.5 or lower than 0.5, and based on this you would predict that everything that is in this area is going to break, and that everything that is in this area is not going to break, which in this case would not be a very good model, because you have all those points here, all those examples that tell you that for this applied load, the structure is very likely to break. So in this case, a linear model is not the best choice because it's going to be very influenced by those time of extreme points. And the hypothesis is just not the right type of hypothesis for a classification model. In a classification model, you have only two possible values, 0 or 1. But in this case, the linear model will go between minus infinity to plus infinity. So clearly, this is not the best possible hypothesis for these types of problem. So here, rather, what we are going to do is to say, if we take exactly the same data, so same thing, you have some given feature x. This is still the applied load. And then you have the given label y, which is going to be either equal to 0 or equal to 1, where 1 means that the structure breaks for this given applied load, and 0 means that the structure does not break. Okay, and the same thing, so we have the same training example. So you have different examples, different measurements of for the given structure. You measured the same structure with different loads, and sometimes it fails, sometimes it doesn't fail. So now the question is, based on those training examples, can I come up with a better hypothesis? So hypothesis that's going to be better at predicting if this structure is going to break or not for this given load. And when you use logistic regression, the types of hypothesis that you are going to use is not going to be a linear hypothesis anymore. You are going to use a sigmoid function as the hypothesis. So the sigmoid function, we already saw it in the chapter on artificial neural networks. That's the same function that is used for the activation function in artificial neural network. And the sigmoid is going to be equal to 0 when x is very small. And then at some point will start to increase, and then will become equal to 1 when x is very large. So that's going to be, in this case, the hypothesis is going to be a sigmoid function, and that's a better choice for a classification model because the sigmoid can be equal to +1 or -1. It can be equal to a given value between 0 and 1. So it's a good choice for a classification problem. It cannot be larger than +1, or it cannot be lower than 0. So that's a good thing. And as we are going to see, it's going to this sigmoid tells you the probability that the structure is going to break. It's telling you that if the sigmoid is very large, very close to 1, then there is a very high probability that the structure is going to break for this load. And on the other hand, if the sigmoid function becomes very close to 0, then there is a very low probability that the structure is going to break. So the value of this sigmoid function is directly giving you the probability to belong to this class 1. So as a reminder, the sigmoid function that is used as an hypothesis here, the formula for a sigmoid function is that this function depends on a variable z, and the formula of the sigmoid function is 1 over 1 plus exponential minus z. So if you look at this function and what it looks like when you plot it, if you take a very low value of z, when z goes to minus infinity, then exponential minus z becomes plus infinity. So exponential of minus z becomes equal to plus infinity. So you have 1 divided by plus infinity. So the sigmoid becomes very close to 0 at very low value of z. Then, on the other hand, if z becomes very large, then minus z becomes very close to minus infinity. So exponential minus z becomes very close to 0. In this case, you have 1 divided by 1. So your sigmoid becomes equal to 1. and then so that's what you will get at very large z. The sigmoid becomes close to 1. And when you take z equals 0, exponential 0 is equal to 1, so the sigmoid becomes equal to 1 divided by 1 plus 1, which is 0.5, 1/2. So the sigmoid looks like this. It's equal to 0 at very low z, then it will start to increase exponentially. It becomes 0.5 when z equals 0, and then it saturates, it plateaus at g of z is equal to 1. The value of the sigmoid becomes equal to 1 when z becomes very large. So we cannot directly use simply this sigmoid, because here, like, the sigmoid is always equal to the same value. There is only one type of sigmoid function. So we need to add some fitting coefficients so that we can use this sigmoid function as the hypothesis to make the classification, to predict for the value of a given feature is what is going to be the class. Is the class going to be 0 or is the class going to be 1? So here what we are going to do for this is to do a transformation, which is that we are going to say that z is going to be a function of x, and we are going to say that z is going to be the same as in linear regression. We are going to say that z is going to be the transpose of theta, where theta is going to be the matrix, the vector matrix that corresponds to the different coefficients of the model, and x is the list of the features, x1, x2, x3, etc. So for example, if you have only one feature, then z is going to be theta naught plus theta 1x, like the typical linear function when you have only one features. And so based on this, it means that now the function for the sigmoid, when you express it in terms of x, so you are going to replace z by x. So now if I express it, it becomes 1 over 1 plus exponential minus theta naught minus theta 1x. And one way you can rewrite this to try to better understand what this function is about, so you can rewrite this as 1 divided by 1 plus exponential. We can put theta 1 in factor, so you have x minus theta naught divided by theta 1. So that's one way to rewrite it. That makes it a little bit easier to understand what this function is about. Why? Because now if we plot this function as a function of x, so it's still going to look like a sigmoid function, but there is two things that are going to change. The thing that is not changing is that the sigmoid is still going to go between 0 and 1, so this is not going to change. But the first thing that is changing is at which point is this sigmoid going to be equal to 0.5 now. So the sigmoid is going to be equal to 0.5 when the exponential terms becomes equal to 0. So when this term here, when this exponential becomes equal to 1, so when what comes at the inside the exponential becomes equal to 0, this is when you will have 1 divided by 1 plus 1. So this is when the sigmoid will be equal to 0.5, which is going to be the limit between the two classes. So this is going to be true when what comes inside the exponential becomes 0, and this is going to be true when x becomes equal to minus theta naught divided by theta 1. So now the point at which you will have the limit between the two classes, the point at which the sigmoid will cross the threshold value of 0.5, will be not at 0 like in the case of a regular sigmoid function, but at the point where x becomes equal to minus theta naught divided by theta 1. So this term here gives you the threshold at which the sigmoid is going to be equal to 0.5. So now it means that now if you plot the sigmoid rather than looking like a function like this that is going to cross the value of 0.5 for z equals 0, now the sigmoid will look like this. So it's going to still look like something that is very close to 0 when x is very small. Then the sigmoid is going to increase. It's going to go through the value of 0.5 when x is equal to minus theta naught divided by theta 1. And then at high x, the sigmoid is going to be equal to increase, and plateau towards y equal 1. And the second thing that is different with respect to a regular sigmoid function is we have a term theta 1 here in front of x, which we don't have inside a regular sigmoid function. So this theta term is going to stretch or to compress the sigmoid function. So let me show you an example. If you take a very high value of theta 1, it means that as soon as x becomes a little bit positive, as soon as this term here becomes a little bit positive, then very quickly the exponential will become very small, because you are multiplying this term here that depends on x by a very large value of theta 1. So you will have an exponential of minus a very large number. So the exponential will be 0 very quickly. So when you multiply by a very large value for theta 1, then as soon as x becomes slightly larger than theta naught divided by theta 1, exponential will become very close to 0, and then it means that the sigmoid function will become very close to 1. On the other hand, as soon as x becomes slightly smaller than minus theta naught divided by theta 1, again you will multiply it by a very large number theta 1. And in this case, it means that what is inside the exponential is going to be very large. So it means that you will your sigmoid will become very close to 0. So if you are using a very large value for theta 1, then the sigmoid is going to be compressed. The sigmoid is still going to be equal to 0.5 when x is equal to minus theta naught divided by theta 1. This doesn't change. But as soon as x becomes slightly smaller very quickly, the sigmoid is going to be equal to 0. And as soon as x becomes slightly larger than this threshold, then the sigmoid will become close to 1. So this is what you will get when you use a large value of theta 1. And on the other hand, if you use a very low value of theta 1, like a value that is close to 0, then it's going to stretch the centroid. Now it's going to, you will need, starting from this point, you will need to decrease x a lot to decrease the value of the centroid, and you will need to increase x a lot to increase the value of the centroid. So this is what happens when you use a low value for theta 1, a value that is very close to 0. So altogether, we have those two parameters. We have theta 1 and theta naught. So theta 1, the role of theta 1 will be to either stretch or compress the sigmoid, and the effect of this is that when you compress the sigmoid, then very quickly you move from something where you predict that this is class 0, and then very suddenly you move to predict that this is class 1. It means that the probability to be class 0 or class 1 is going to very suddenly change from around this threshold value. So it means that in this case, what you are going to do is you are going to predict that the probability to be 0 or 1 is going to suddenly change around this threshold value. On the other hand, when you use a low value of theta 1, then you are going to predict that the probability to be the 1 is going to be 0, 0, and then going to slightly increase as you increase x, and this probability slightly increase as x is increasing. So when you change the value of theta 1, what you are controlling is the sharpness of the classification of the model. You are predicting whether this probability is going to sharply change from being 0 to 1, or to changing more smoothly, more gradually between 0 to 1. So you are influencing the sharpness of the model, the sharpness of the hypothesis. And then you have this second term, which is minus theta naught divided by theta 1, which mostly going to depend on theta naught. This one is this threshold term. So if you decrease this term or increase this term, what you are going to change is to change the value of the threshold value of x, for which your model is going to either predict a class 0 or a class 1. So you change the threshold value of the features, for which if this feature is higher than this threshold, then the model is going to predict that the label is going to be class 1. You are going to be in this domain. And on the other hand, if the value of x, if the value of the feature x is lower than this threshold, then you are going to predict that for this feature you have a class 0. So by changing the value of theta naught and the value of this ratio minus theta naught divided by theta 1, you change the position of the threshold, where your model will suddenly predict that instead of being class 0, it's going to be class 1. And in this case, the classification will be based on the value of the hypothesis. So you take the value of the hypothesis g. If it's larger than 0.5, then the prediction is that that you have an observation that corresponds to a label being class 1. On the other hand, if the hypothesis is lower than 0.5, then the prediction is that it's going to be a class 0. In logistic regression, like, there is not just this value that matters. The value of the hypothesis itself, so the value of g of x, is also interesting because it's telling you the probability to be class 1. So if you are if the hypothesis is very large, then it means that you have a very high probability to be class 1. And on the other hand, if the hypothesis is very small, then it means that you have a very low probability to be class 1. And for a classification model, what you will say is that if this probability is larger than 50%, then you will predict that it is class 1. If the probability is lower than 50%, then you will predict that it is class 0. So in practice, how does it work? In practice, you start with your training example. You have, for different values of the feature x, you have a different label y. You have a few training example like this, where sometimes the label is 0, class 0, sometimes it's class 1, and so you have different measurements as well. And what you need to find in the case of the logistic regression is you need to find what are the optimal values of the coefficient theta naught and theta 1. This is what the two coefficients that you get if you have only one features. You need to find what is going to be the optimal values of theta 1 and theta naught that will result in the sigmoid that fit the data the best. So it's similar to a linear regression problem, in the sense that in linear regression it's the same thing. You have some features that are related to some label, and you want to interpolate this by a line, and you will need to find the best values of theta naught, which is the intercept, and the best values of theta 1, which is the slope. And you need to find what's the best value for those coefficients that will minimize the error of the model. So here it's going to be the same, except that now theta 1 and theta naught are controlling the shape and the position of this sigmoid function, and you want to adjust the values of theta 1 and theta naught that will maximize the accuracy of the model. So here, this is what it looks like when there is only one feature x, so that is to say only one dimension. But if you have several features, for example, if you have two features, you can still apply the same idea, but now it becomes harder to represent. So now let's assume that you have two features. So you have a given feature x1 in this case, though. So x1 is still going to be the applied load, the load that you applied to your structure. And then you have a second feature that becomes influential, which is going to be, in this case, the temperature. Now you're going to take into account the effect of the temperature, because maybe if the temperature becomes very high, you will have a higher risk that your structure is going to break for a given load. So now you're going to take those two features to predict whether your given structure is going to break or not. So now, same thing, you will need different training examples. So you will make some measurements. You will look at your structure and you will make some measurements. So sometimes if it's at high temperature, then the structure is going to break even at a low applied load. But if the temperature is very low, then you will need a very high applied load to break it. And then so you will measure different points like this, where sometimes the structure is going to break. So this is when the measurement that corresponds to a case where it breaks. And then you have some other measurements that corresponds to a case when the structure does not break. So sometimes when you have a very low applied load, the structure does not break, or when the temperature is very low, then the structure also doesn't break. So in this case, those are the corresponds to the measurement where the label of the data does not break. And then in this case, the goal of the logistic regression will be to find again the best model that is going to describe whether for a given combination of features, if the structure is going to break or not. So in the case of when you have only one feature, the only thing that you do is to look at the value of your hypothesis, and you look at, is my hypothesis larger than 0.5 or lower than 0.5. This is giving you what we call the decision boundary. This is the threshold. In this case, the threshold is this minus theta naught divided by theta 1. And if x is larger than this decision boundary, then it's going to be class 1. If x is lower than this decision boundary, then it's going to be labeled as class 0. So in the case of when you have one features, then the decision boundary is just 1 point, one threshold value. Now, if you have two features, the decision boundary will become a line. Now, the decision boundary that will dictate whether your model predicts that it's going to break or not, now it's going to be a line like this that separates the two classes. So this is, in this case, going to be the decision boundary in 2 dimensions. So this is what you will get when you have two features. The decision boundary is going to look like a line. So in general, when you have n features, so when you have a model that have n dimension, the dimension of the decision boundary is always going to be n minus 1. So if you have only one feature, so a 1D model, then the decision boundary is just going to be one single number. So that's 1 point, that's a dimension of 0. Now you have two features, so n equal 2, then the decision boundary now becomes a line. A line has one dimension. If you had 3 different features like this, then the decision boundary will be a plane like this. So if you had 3 features, the dimension of the decision boundary would be a surface with a dimension of 2. So the dimension of the decision boundary is always the dimension, the number of features minus 1. So when you have an object like this that has a dimension that is equal to the dimension of the space minus 1, it's called an hyperplane. So a hyperplane is when the dimension of this boundary is the dimension of the total space minus 1. So when you have a 3D feature space, so when you have 3 features, then it means that the dimension of the decision plane, the decision boundary, is a plane which has a 2D, which is a 2D object. So that's a hyperplane. The dimension is always n minus 1 when n is the number of features. So n is the dimension of the feature space, the space of all the features, and n minus 1 is going to be the dimension of the hyperplane that corresponds to the decision boundary. And then the good thing about this classification model is once you have defined your decision boundary, once you have parameterized your decision boundary, then you can use this model to make some prediction. In the case of if you have one features, then you can say that now if I have a given feature like this, based on the value of this feature, I can look at what my model is predicting, and if the model is lower than the decision boundary or higher than the decision boundary, then it's gonna either predict class 0 or class 1. So for example, if you take 1 point here, it's predicting that it's gonna be class 1, that's gonna be predicted to be class 1. And then if you have another point here, then you are going to predict that it's sorry, I said exactly the opposite. So here, when you have a given feature here, you're going to be predicting that it's a class 0. And when you have a given feature, when the value of the feature is here, what your model is predicting, you are on the right of the decision boundary. So now you are predicting that the value of the class is 1. That's the same thing in 2 dimension. Now you take for a given structure, you can look for a given applied load, and for a given temperature, you can look at what is the model predicting. And in this case, the model is going to be on the right. The prediction is going to be on the right of the decision boundary. So you will predict that for this value of the absolute load and for this value of the temperature, then your prediction is that the class is break. So you are predicting that the structure is going to break. So once you have parameterized your model, once you have parameterized the position of the decision boundary, then you can use this model to make some prediction on whether this structure is going to break or not as a function of the applied load, as a function of the temperature. So far in the example that we saw, we talked about linear model. When I say linear model, it means that the hypothesis of the model only depends on linearly on the values of the features. It only depends on the x1 and x2. So it means that, for example, if you have if we retake this example of the 2 features x1 and x2, if we are taking a linear model, a linear logistic regression, then it means that you will assume that for the given observation, when you have the different classes like this, the assumption of a linear logistic regression model is that the decision boundary is going to be a line. So as a reminder, the decision boundary is obtained when the hypothesis of the linear logistic regression, which is 1 divided by 1 plus exponential minus z. So the decision boundary corresponds to when this hypothesis becomes equal to 0.5. This is when you have the transition from class 0 to class 1. And then, so this happens when z is equal to 0. So the z equal to 0 corresponds to the decision boundary. And in this case, what we said is that in this case we have assumed that z is equal to theta, the transpose of theta times x. So in this case, since there is a 2 features, then it means that in this case z would be equal to theta naught plus theta 1 x1 plus theta 2 x2, which is the same kind of hypothesis for a linear regression model. And then, so the decision boundary is obtained when z is equal to 0. So this, in this case, would be the equation of the decision boundary. So this is the equation of a line. That's an equation that depends on x1 and x2. That's just a polynomial that relates x1 and x2. That's an equation of a line. So this is the equation of the decision boundary. This is the equation of the hyperplane that corresponds to the decision boundary. And in this case, it's a linear decision boundary because it only depends on x1 and x2, not on other terms like x1 square, x2 square, or x1 times x2. But that's not a prime. Like it's in exactly the same case as for linear regression. You can create new features. You can do some feature engineering. If the data appears to be non-linear, then it might be a good idea to do some feature engineering to create new features, and you can just create new feature that you are going to call x3, x4, etc. And maybe those features are going to be x1 square, x2 square, etc. So you can always transform logistic regression into a non-linear method just by creating some new features, in the same way that you can still use linear regression to fit a non-linear regression problem just by doing some feature engineering, by creating some new features that are x1, x cube, x to the power 2, 3, 4, 5, etc. So one example for this that is pretty common is if you have a case like this, when you have two features x1 and x2, and for example you have several cases of observation measurements like this when it is class 0, and then you have some other measurements like this when this time for those measurements you get a class that is equal to 1. So now the class is 1. So in this case, clearly in this case you will not be able to find a linear decision boundary, a linear hyperplane that can separate class 1 from class 0. So that's not going to be possible in this case. So in this case, you need to create some new features. And here you can get some intuition and see that in this case, the right decision boundary, the right hyperplane should be a circle like this. That's going to be the best possible decision boundary in this case. So in this case, like we know the equation of a circle. So for example, if this is r, the radius of the circle, the equation of this circle is x1 square plus x2 square equal r square. So that's the equation of the circle if the circle is centered around 0, 0. It means that in this case now, the equation of your decision boundary, if you want, you can rewrite it as x1 square plus x2 square minus r square is equal to 0. So it means that now, if you want logistic regression to be able to fit this kind of decision boundary, you will need a new you will need to introduce x1 square as a new features. You will need to introduce x2 square as a new features. And for example, now you can fit a model that will be theta naught plus theta 1 x1 square plus theta 2 x2 square. So something that is very similar to the linear model that you use for linear logistic regression, but now your new features are going to be x1 square and x2 square, and in this case the right coefficients that that you should find that's going to give you the most optimal model would be that theta naught is equal to minus r. That's how you can get this term here, and theta 1 equals 0. That's how you can get this term here. So theta 1 equal 1, not 0, sorry. And then you would find that theta 2 is also going to be close to 1. That's how you find this term. So in this case, this would be the model that you would be using, and this equation here would be the new equation of the hyperplane, the new equation of the decision boundary that allows you to predict for a given combination of the features x1 and x2 whether you will predict that the label corresponding to those features is class 1 or class 0. So now the goal is the same as for a conventional linear regression model. Is you have some data, some training data. You want to use those data to train your model. And in this case, training the model means to find the best possible values for the coefficient theta that will offer the best classification, the most robust classification, in the very same way that in a linear regression model, you want to find the best possible values for the coefficient theta that will give you the most accurate regression model. So for this, to find the optimal values for the coefficient theta, it's going to be the same approach as in linear regression. We are going to define a cost function that tells you how good the model is, and then we will need to minimize this cost function to find a model that has a cost function that is as low as possible, which will mean that the model is as good as possible. So we will need to change the value of the parameters theta, not theta 1, theta 2, and we will need to adjust the values of those coefficients in order to minimize as much as possible the cost function. So as a reminder, in the case of linear regression, the cost function that we define in the case of linear regression was that if you have a linear model like this with a given model, and then you have some given training example like this. In this case, the cost function that we defined was the mean squared error, where we take, in this case, the difference for each training example I. You have m training example. M is the number of training example, and what you are going to do is, for each training example, you are going to calculate the difference between the predicted value, the value predicted by the model. So the value predicted by the model is the value of the hypothesis. So for a given training example xi, for example number I, the predicted value is the value of the hypothesis for a given x by the model, and then you take the square difference with the true label for this function, the true value of y. You take the difference, you take the square difference. And in this case, one way that we can write the cost function for linear regression is to say that the cost associated with training number I is equal to this square difference divided by 2, so that after that, the total cross function as a function of theta can be expressed simply as the sum over all the training example of the costs associated to each training example I divided by the number of training examples. So here, if you define the cost like this, if you say that the cost associated for a given example I is going to be the square difference divided by 2, then at the end you can say that your total cost function is going to be the sum of all the cost function associated to each training example I divided by m. As if you replace the cost by this expression, then you find the expression of the mean square difference, the mean square error that we used for the linear regression, which is the sum of the square difference divided by 2m. So one way to express this is just to express the cost associated to just the example I, and then just say that the total cost function is going to be the average of all the costs, the sum of the costs divided by the number of training example. So now when we move to logistic regression, we will not be able to use the same expression for the cost function. Why? Because now the classification model looks very different. Now your hypothesis, your label y can only be equal to 0 or 1 and nothing in between. And now you have a different example like this. Then you have your model that looks like that. And if you were to do the same, if you wanted to just take the square difference, then that would not be ideal, because for most of the cases the difference would be very small, because the true value can be either y equals 0 or y equal 1, but very quickly your model will become equal to 0 or equal to 1, and only the points that are the closest to the decision boundary would actually contribute to the cost function. The other problem with this is that if we define the cost function like this, it's not going to be convex. It means that there will be more than one possible values for the coefficient theta 1 and theta naught that will give you a local minimum. There could be more than one optimal values of theta naught and theta 1. It means that the cost function would not be a convex function of theta 1 and theta naught. Like what we want is a cost function that looks like this. When we plot the cost function as a function of theta 1, for example, we want the function to be convex like this, so that there is only one optimal theta 1 values. But if we use the mean square error, then you can have a function that is potentially not convex like this, with different local minima, different values of theta 1 that can give you a local minimum for the cost function. So this would be a problem, because it means that we would not be able to use the conjugate, the steepest gradient, the gradient descent method. In this case, you would get stuck into some local minima. So we need to define the cost function for logistic regression in a different way, so that we still end up with a convex cost function. And in this case, rather than using the mean square error, the cost function that we are going to use, the cost function that works the best for linear regression, is the cross entropy. So if you think about the cross entropy, it's actually pretty similar formula that for the regular entropy that you find in thermodynamics. In this case, it's a measure of the disorder, or it's a measure of the how good or how bad is the prediction of the models. So let's just see what the formula for this cost function is, and then we will just try to understand it. So the formula for the cost function in this case, for the cross entropy, is that the cost function associated with example I will be given by this value. But in this case, there is two possible values. There is two possible values depending on whether the true label for y is equal to 1, or whether the true label is equal to 0. So if you have a point for which the true value of y for this point is 1, so if it's a point that truly belong to class 1, then to check how good your model is, rather than measuring the square difference between the prediction of your model and the values of y, what you will measure is the minus the log of the value of the hypothesis predicted by your model for xi. So let me just give you the formula first, and then we will see why this formula is a good choice. And then when now you have a point that is a true point that truly belongs to class 0, then the formula now will be different. The formula that will correspond to the cost of your model for training I is going to be equal to minus the log of 1 minus the value of the hypothesis for example xi. So let's see what this means. So let's just look at the two cases where y is equal to 1, when it's a point that truly belongs to class 1, where the true class of this example is 1. And we are going to look at the second case where the true class for this example is 0. So let's look at first case when the true value for the label is 1, and second case we will see the case where the true value for the label is 0. And for this, what we are going to do to understand what this cost corresponds to is that we're going to plot the value of the cost that the associated to the model as a function of the value of the hypothesis predicted by this model. And we are going to do the same for the two cases where the true class of this value is 1, or the true class of this value is 0. Okay, so let's start first with the case where the true class of this point is 1. Then what we say is that the expression of the cost associated to this given point is going to be minus the log of the value of the hypothesis. So what does it mean? It means that if in this case the true value of the class is 1, so the hypothesis can change between 0 and 1, but in this case 1 is the true value. If your model was perfect, it would predict that the hypothesis is 1 because that the true label is indeed 1. So indeed, in this case, if the hypothesis is equal to 1, then you take minus the log of the hypothesis. The log of 1 is 0, so you find that in this case your cost would be 0. So if your model predicts that indeed the label is predicted to be 1, then the cost is 0. It means that your model is perfect. And then if your model, instead of predicting that the hypothesis for this point is equal to 1, if the model is predicting that the hypothesis is slightly below 1, then you are calculating the minus the log of something that is slightly smaller than 1. So the log of something slightly smaller than 1 will become more and more negative as what's inside the log is becoming more and more smaller than 1. So now you take the log of this value, and then you take the minus of the log. It means that the minus of the log will become more and more positive as you as the hypothesis becomes smaller than 1. So it means that when your model predicts that the hypothesis is smaller than 1, then the cost associated to these data points will become larger and larger. And if your model predicts that the hypothesis is 0, then the cost associated would be plus infinity. If the hypothesis becomes 0, minus the log of 0 is minus infinity. The log of 0 would be minus infinity, so minus the log of 0 would be plus infinity. So it means that if your model is making the right prediction, then the cost is 0, and the more your model makes the wrong prediction, the more the hypothesis is far away from the true label y equal 1, then the more the cost is going to increase, the more you will have a high cost associated with this training example. So now let's look at the second case, where now you have a point that is truly equal to 0. So you have a point like this that is truly equal to 0, and we want to see what is going to be the cost as a function of what the model is predicting. So in this case, so the hypothesis of the model can still go between 0 and 1. That's the value of the sigmoid. It can still go between 0 and 1. In this case, if the model is perfect, so if the model is perfect, it would predict that the hypothesis is 0, because that's the true label of the data. So if the hypothesis is 0, then 1 minus 0 would be equal to 1. Then you would take the log of 1, which is 0. So minus the log of 1 would still be 0. So in this case, the cost from your model would be 0 if it was perfect. If it was predicting that indeed the label is 0, then the cost would be 0. And same thing here, the more you increase the hypothesis, the more the hypothesis becomes slightly larger than 0, then you will calculate the log of something that becomes slightly smaller than 1. So again, when you take minus the log of something slightly lower than 1, then the log minus the log will increase, and it's going to increase like this, and it's going to continue increasing as the hypothesis becomes 0. And when the hypothesis was, if it becomes 1, then the cost would become infinite. So if your model is predicting a hypothesis of 1, despite the fact that the true value of the label for this data point is actually 0, then that would be an infinite cost. So in this case, this is what would happen. If the hypothesis is 1, then you have 1 minus 1 equals 0, minus the log of 0 would give you plus infinity. So the cost would be plus infinity. So this shows you, like, the more the model is right, the lower the cost. And the more the model deviate from this right value for the label, the more the cost will increase. So that's still the same spirit as the mean square error, is that the further the model is from the true label, the more the cost will increase. But it's a slightly different definition than the mean square error. That's a definition that's, in this case, is going to give you a convex function. When you will calculate if you were to plot the value of the cost function as a function of theta 1, as a function of theta naught, then you would find a cost function like this with only one single minimum at the optimal value for this model. So in this case, to summarize the cost function for logistic regression, so we said that the cost associated to each training example is going to be the minus the log of the hypothesis for a given value of the feature. This is the value if the true label is 1, and then the value of the cost function is going to be minus the log of 1 minus the hypothesis for this value of the feature if the true label is 0. So this is the cost function, and in this case, if you want to get the total cost function, then what you will do is simply to do the average of the cost associated to each training example. So you will do the sum between 1 equal 1 to m, where m is the number of training example, and you divide by m. This is the average. So this is the same idea for linear regression. You take the average, you sum all the costs, you divide by the number of points. That gives you the average cost per point. So there is one way that you can write this cost function in a slightly more compact way, rather than having those two cases here. It's more like a trick, but one way that you can write this is to say that the cost function theta is going to be 1 divided by m times the sum over all the training example of, and then you will write the cost function, the value of the cost function for each training example. And here, if you want to directly have a compact form that can take into account those two cases, one way that we can write this is as follows. So what I'm going to do is I'm going to write it first, and then we will see that indeed what I just wrote is equivalent to the two cases that I wrote above. So one way that you can write this is to say that it's going to be equal to minus the value of the true label y for this example number I, times the value of the cost function that I have here, which is the log of the hypothesis for the value of the feature x, minus 1 minus y, where y is still the true value of the label associated to the training number I, times the log of so this term now, the log of 1 minus the hypothesis associated to the training example I. So why is this exactly the same thing as what I have here? Because there is only two cases. Again, y can only be equal to plus 1, or can only be equal to 0. So if if y is equal 1, then this entire term is going to disappear. This entire term is going to be equal to 0 if y is equal to 1. Why? Because this term here becomes equal to 0. So when y is equal to 1, then this entire term becomes equal to 0, and then you find in this case that the cost function is simply equal to this one when y is equal to 1. And then the second case is that if y is now equal to plus to 0, if the true value of the label is equal to 0, now this term is going to be equal to 0. Now if y is equal to 0, then this entire term is going to be equal to 0. You multiply by 0, so this entire term is going to be equal to 0. This is, now you will find only this term which corresponds to this term. Why? Because now this y is equal to 0, so you have only 1 times the log of 1 minus the hypothesis, which is exactly this term here. So if you write it as follows, so if you write this expression like this, with those two terms, and you multiply the value by y in this case and by 1 minus y, then you get a more compact function that is going to be true for both cases. It's true when y equal to 1, it's true when y equal to 0, and since there is only those two cases in this case in the classification problem, then this expression gives you the cost function associated to logistic regression that always work whatever the value of the label, the true value of the label is. So now that you have found an expression for the cost function, then the idea is very similar as for linear regression, is you have a given cost function. This cost function only depends on theta, like the values of y, the values of x, those are the training examples, so this is fixed. The only thing that can vary is theta, and your goal is going to find the values of theta, to find the values of theta 1 and theta naught, or theta 2, theta 3, like the values of all the theta that will minimize the cost function. So this is exactly the same as what we saw for linear regression. You have a given cost function, you want to find the values of theta that will minimize this cost function. So for this you can still use the same algorithm, like for example the gradient descent algorithm, which is going to be like if you have a given values for the cost function like this, you will look at the value as a function of theta, and basically you will look at calculate the gradient, so you will calculate the derivative of the cost function with respect to all the theta, and then you will always move in the negative, the direction of the negative gradient. So if you calculate here, the gradient is pointing towards the right, so you will move towards the left. You always go in the direction that minimizes the cost function. So there's one problem we haven't talked about so far, which is a similar problem that we faced in polynomial regression and in artificial neural network, which is the problem of finding the best balance between underfitted and overfitted model. So we need to make sure that our model is not exhibiting underfitting, being too simple, or overfitting by being too complex. So for example, let's take 3 examples. So let's assume that we have 2 features, x1 and x2, and then so you have some training examples. So then in one case you have some example of observation for class 1 and then or class 0, and then you have some observation for class 1, for example. Okay, and then in the same case as linear regression, when you do this, you will necessarily, if you are taking some real world data, you will necessarily have a little bit of noise. So you will have some cases where sometimes you will have an example of a point here that is classified as label 1, that is to say class 1, although probably it should not. It should be actually a class 0. And then same thing, you will probably have some example of points that are classified that are mislabeled like this, or some outliers, some noise. When you deal with real world data, you have always some noise like this. It's never a perfect classification with clearly different, clearly separated classes like this. So let's say in this case, like how should we deal with this, and how should we find the best decision boundary for this type of model, this type of data set. So here what happens, if I use a degree 1 model, so just purely linear logistic regression, then what I will find is that the decision boundary will just be a linear line like this, and probably here that would be an example of underfitted model. Why? Because it looks like this model would be too simple in this case. Like it doesn't seem like it's capturing the fact that the data appears to be non-linear, that there is a non-linear, that the boundary between the red points and the blue points should not be a linear function, but actually a non-linear function, maybe a quadratic function. On the other hand, if you now do a very high degree, so if you do a high degree model where you end up with a very complex function, a very complex shape for your hyperplane, for the decision boundary, now if you use a very high degree, you run the risk to have an overfitted model. What it's going to look like is that your model is going to be very complex, and it's going to try to minimize the cost function. And the way to minimize the cost function is to make sure that the data points are always properly classified, that the red points are always on the left of the decision boundary, and that the blue points are always on the right of the decision boundary. That's the way you minimize the cost function. So in this case, to minimize the cost function, what the model can potentially look like is something like this, where the model is going to make a lot of effort like this to make sure it never misclassify any points. So in this case, that would be an example of overfitted model, because that's a model that is clearly too complex. And that's not good, because if you have an underfitted model, that is certainly not a good thing, because it means that now if you try to assess what the model is predicting from this point, it's going to predict that it should be classified as blue, although it's actually pretty close to the other red point, so it should probably be classified as red. And in this case, when you have an overfitted model, that's the same thing. Now if you want to predict what the model is predicting for this point here, like clearly it should be a blue point, it should be a class 1, but the model is actually going to predict that it's a red point, like the class 0 point, just because it's overfitted and is too deformed. So in this case, most likely the most optimal model would be something of degree 2, something that probably look like this. It's not going to be a perfect model because there's going to be a few misclassified points, but that's nevertheless going to be the most robust model that in the future, if you take a point here, it's going to predict that indeed it should be red. If you take a point here, it's going to predict that indeed it should be blue. So that's going to be a more robust model to predict for the future based on the values of the features x1 and x2. It's going to tell you a prediction of whether the class should be red or blue, class should be 0 or 1 in a more robust way than if you have an underfitted model that is too simple in this case, or a model that is too complex. So in this case, in between would be the optimal degree of complexity for your model, optimal degree of complexity that minimizes the risk of overfitting and minimizes the risk of overfitting. Both minimize underfitting and overfitting, the best optimal degree of complexity for the model. So when you have an underfitted model, the way you can avoid this is to make the model more complex. So to do some feature engineering, creating some new features, having a more non-linear model. So that's typically easy to solve when you have an underfitted model, assuming that you can create some new features that can fix the issue. And if you have an overfitted model, then the way to make sure that the model is not overfitted is going to be exactly the same way as when we used lasso. We are going to use some regularization. The regularization is going to put, in the same case as lasso, is going to put an extra weight on the coefficient. And if a coefficient is not really helpful at classifying the points in the data set, then it's going to be disappearing. It's going to disappear. It's going to be put to 0, so that the cost associated to this coefficient is going to be reduced to 0. So here we are going to do exactly the same thing as in lasso. We are going to add a regularization term in the cost function. We are going to change slightly the cost function of logistic regression to add a penalty associated to the coefficient. So this term, what it will do is it will try to reduce as much as possible the number of coefficients to try to reduce the value of this penalty without compromising the accuracy of the model. So in this case, it's going to be exactly the same spirit as for the lasso, the cost function in lasso. So we start with the cost function of logistic regression, which again, as a reminder, the cost function in this case is 1/m, the number of training example, times the sum over all the training example of minus y times the log of the hypothesis of the model minus the other term that corresponds when y is equal to 0. So the other term is like this: 1 minus y times the log of 1 minus the hypothesis. So that's the cross entropy cost function, and you sum over all those costs for all the training example y. You take the average. That gives you the cost function in linear regression, in logistic regression, sorry. And then if you want to add a term, an additional term corresponding to the regularization, then you are going to do the same as in lasso. You are going to add a term that would be equal to exactly the same as in lasso, a term that is equal to lambda divided by 2m times the sum over all the coefficients. So if you have n coefficients, so you will do a sum of all the coefficient theta j to the square. You will take the square of all the coefficients, sum all those coefficients, and multiply by the regularization constant lambda. And this term here is going to be the regularization term. So that's going to be an additional penalty to the cost function. And since your goal is to minimize the cost function, then you will want to when you run your gradient descent algorithm, you want to minimize the cost function. You want to find the value of the coefficient theta that minimize the cost function. So if you have a very high lambda, then you will put a very high penalty. So you will, in this case, in order to minimize the cost function, you will need to reduce the number of parameters theta that are not equal to 0. So you will have just a few parameters theta that are equal to 0, just the most important. And the more you reduce lambda, the more you will have more and more complex model. You will reduce, if you reduce lambda, you will reduce the amount of the penalty associated to the coefficient. So you will have more and more coefficient theta j that becomes equal to non-zero. So you will have more and more complexity in your model. And at the end, if lambda is equal to 0, then it means that there is just no penalty at all. There is no regularization. So you just find again the regular cost function of linear logistic regression. So it's going to be exactly the same idea as in lasso. The higher is the value of lambda, the more penalty you put. So the more simple the model will become. And the lower the value of lambda, then the more complex the model will become. And same thing, so lambda in this case is a hyperparameter of the model. So you will need to find what is the best value of lambda that minimizes the cost function for a validation set. So you will still need to do the same thing, train the model based on a given training set, then validate the model based on a validation set to find the best values of the coefficient lambda. So far all the cases that we talked about are cases of binary classification, where the class can be either 0 or 1. There is only two possible classes. So now what we are going to talk about is briefly talk about the case of multiclass classification, which is when you have more than just one class, when you have class 1, class 2, class 3, etc. So the good news is that typically when you have a multi-class classification, it's going to be exactly the same thing as a binary class classification. Like you will try to decompose the model, to simplify the model, to simplify it in terms of just binary classification model. So let's just take some examples. So for example, an example of multi-class classification is if you try to predict the weather forecast. In this case, it's not just 0, 1. There can be several possibilities for the weather. It can be sunny, can be cloudy, can be rainy, can be snowy. So in this case, you will have 4 different classes, 4 different possible classes. Let's take another example. So for example, let's assume that you want to predict the type of cement. Let's assume that you have a section of different cement, and you want to predict whether you want to have a model that can predict whether it's going to be cement type 1, type 2, or type 3. And in this case, the different features that you will use is 2 features, x1 and x2, where x1 is going to be the strength of the concrete that you make after 7 days. So you will mix your cement with some aggregates, with some water, and you will measure its strength after 7 days. And the second features will be again the strength of the concrete, but this time after 28 days. Which are 2 different standard measurements of the performance of a concrete. After 7 days, it's telling you the constructability of the concrete, and after 28 days, it's telling you about the long-term performance of this concrete. So let's assume that you want to develop a model that can predict, based on the value of the strength at 7 days and at 28 days, you want to predict whether this concrete is type 1, type 2, or type 3. So for this same thing, you need some training examples. So let's assume that you have different measurements for different concrete. And for example, when it's type 1, so you get some different measurement like this. So that those would be some example of measurement for type 1 concrete, which would have an intermediate strength at 7 days, but a pretty high strength at 28 days. So that's an example of concrete that is gaining a lot of strength after a pretty long time, but maybe doesn't have so much strength at just after 7 days. Then you have some other example of some other types of concrete. That's going to be some example of type 2 concrete, which maybe will have a lot of strength after 7 days. So it's going to have a lot of strength very early, but on the long term, like the strength after 28 days is not going to be as high as the type 1. So those red are going to be some type 1 cement. In this case, those are going to be some example of measurement for type 2 cement. And then same thing, you have some example of measurement for type 3 cement, which in this case would just have not only a low value of strength after 7 days, but also a pretty low value of strength after 28 days. So that's going to be some example in this case of some example of type 3 cements, which just don't develop so much strength, whether it's early or after a long time. So here the question is now, based on the values of x1 and x2, how do I predict whether it's a type 1, a type 2, or a type 3 cement? How can I predict and train a model that's based on the values of x1 and x2 is going to tell me not if it's just class 0 or 1, but which class among those 3 classes does the cement belong to. So for this, one of the approach that we can use, which is actually pretty smart because it simplifies this complex multi-class classification into just a binary classification, is to use the one versus all classification. And the idea of this is that rather than training a single model that can predict whether it's type 1, type 2, type 3, we are going to train 3 different models. So we're going to train a first model for type 1 cement, where we are going to do so a 1 versus all classification. So what we are going to do is to separate the training set into the cement type 1, and then all the other cements we are going to say that those are the others. So we are going to train a model that can classify cement type 1 versus all the others. So in this case, if we do this, the kind of decision boundary that we would find would be probably something like this, where everything that is higher than this would be classified as a type 1, and everything that is lower than this would just be the rest, like everything that is not type 1, either type 2 or type 3. Then, so we are going to repeat this. We are going to repeat that for the type 2. So we're going to train another 1 versus all classification models, where we are going to take we are going to relabel the dataset as either type 2 or everything else, all the rest. And if we do this, the kind of model that we will find is probably going to be something like this, where everything that is on the right is going to be classified as a type 2 if it's on the right, and if it's on the left, it's going to be something else. It's going to be the rest. And then, so we're going to train a third model for the type 3, where this time maybe the model will look like this, where if it's on the left like this, it's going to be classified as a type 3 model, and if it's on the right, then it's going to be the rest. And then, so you will have those 3 models. And now the question is, for once you have those 3 models, if you take now a new point, a new values for the features x1, x2, like what do you predict in this case? So let's take an example for this. So if you take a point here, so most likely it should be a type 1. And let's see what how can we figure out what the model is predicting. What the way we are going to use those 3 models is that, so based on the 3 1 versus all models, so we will have characterized and train 3 different models. Each of those 3 different models will give you their own hypothesis. So you will have the model 1 that will give you a hypothesis number 1 as a function of the value of the features. Then you have model 2 that gives you an hypothesis number 2, and the model 3 that is give you an hypothesis number 3. So if we look at the values of those hypotheses, so we have this this point here, and we want to see what is going to be the hypothesis for this point. So if you take model 1, model 1 is for this point is on the top of the is higher than the decision boundary. So model 1 is going to say, I predict it's a type 1. Then if we look at model 2, model 2 predicts that it's on the left of the decision boundary. So it's predicting that it's something that is the rest, something that is not not a type 2 cement. And then if you look now at what the model model 3 is predicting, we look at if it's on the left or on the right, and in this case again it's predicting that it's the rest. It's predicting that it's not a type 3. It's not a type 3. So in this case, the way we can predict is to look at the hypothesis of those 3 models and take the maximum, to look at which model is predicting the maximum hypothesis. In this case, it's predicting that it's not type 2, that it's not type 3. So it means that the hypothesis is going to be lower than 0.5 in this case. In both cases, you are on the other side of the decision boundary. This one is predicting that it's type 1. It means that the value of the hypothesis for this model is going to be 0.5. So in this case, it means that we are going to predict that indeed it should be a type 1, because we look at the 3 model, we take the model that predicts the highest hypothesis for these data points, and that's the point that we are going to use. We are going to say that it's a type 1, it has a class 1, because the model 1, the model of type 1 versus all, is the one that is predicting the highest hypothesis. Let's take another example, just to show another example where it's not necessarily as obvious as this. Let's take a point maybe like this. So if we take a point like this here, clearly it should be a type 3 like that. That's what it would look as a human. You would say it looks like it's a type 3. So let's see what the model is predicting. First, if we look at the model 1 would think that, okay, it looks like it's higher than the decision boundary. So I predict that it has a fairly high probability to be a type 1. Then if we look at the model for the type 2, then it's very far from the decision boundary. So it's clearly not a type 2. And then if we look at the model for the class 3, then it's pretty far on the left of the hyperplane for the model 3. So there is a pretty high chance that is indeed a class 3. So now if we look at the hypothesis for the 3 models, for type 1, the hypothesis will be slightly larger than 0.5 because it's pretty close to the boundary, slightly on the top of the boundary. So the hypothesis of the logistic regression will be slightly larger than 0.5. If we look at the hypothesis for the model number 2, it's very close to 0 because it's so far away here that the hypothesis, it's a very low probability to be a type 2, so the hypothesis is going to be close to 0. On the other hand, the hypothesis for type 3 is going to be pretty high because it's pretty far from the decision boundary. It's further away from the decision boundary for model 3 than it is of the decision boundary from model 1. So in this case, if you take the maximum hypothesis is going to be offered by the model number 3 because it's further away from the hyperplane of model number 3. So in this case, what the model is going to be predicting is that indeed this point is a type 3. So that's the approach that you can use when you have more than just one class. You can just use this one versus all classification where you just train as many models as you have classes. If you have 3 classes, you need 3 models. If you have 4 classes, you need 4 models. And then you look at the different models, you see which one is predicting the highest hypothesis, which one is predicting a hyperplane that is as far away as possible from the points for which you want to make the prediction. In this case, you take the maximum value of the 3 hypothesis of the 3 model, and that's going to give you the most likely predicted class, which in this case would just be a class 3. So the typical process when you want to develop a classification model, the typical process will be as follows. So you will start by first training your model. So for this, you will train the model. Training the model means finding the most optimal value of theta naught, theta 1, etc. And for this, you will train the model based on a given training set. You will take a fraction of your data. You will take a fraction of the data set, and that's going to be your training set. Then the second step is that you need to make sure your model is not underfitted, not overfitted. So you will need to optimize the hyperparameters like the regularization parameter. So you will need to validate the model. So it means that you will need to optimize the hyperparameters. You will need to, for each of the hyperparameters, you will need to find their optimal values. So for example, for the regularization coefficient lambda, for the maximum degree of the model. And for this, same thing as for polynomial regression. For this, you will select another fraction of the datasets that you will isolate from the training of the model, that you will keep those points hidden from the model when you train it, and you will just use them as a validation set to be able to say whether the model is overfitted or not, and adjust the value of the hyperparameter to make sure that the model is not overfitted. And then the last step is, if you want to see how well is the model doing? Like, what's the accuracy of the model when you are predicting some truly unknown points? Then you will have you will want to finally test the model, and for this, again, you will need to isolate another fraction of the data set. That's going to be this times the test set. We haven't talked so much about this, but typically it's a good idea, even for a linear model or a regression model, it's always a good idea to have 3 types of groups of data. The training set, maybe the training set could be something like maybe 50% could be a good number that you're going to use as a training set. That's the data that you are going to use to train the model, the data that you are going to feed to the gradient descent algorithm to optimize the values of theta naught and theta 1. So that's for the training of the model to optimize theta naught, theta 1, theta 2, etc. Then you need to keep another fraction of the data, maybe let's say 20%, that is going to check that the model is not overfitted, not underfitted. So for example, it's going to now adjust the values of lambda. You are going to use those values to tune the hyperparameters, to tune the degree of complexity of the model. And then the last thing is that you will still want to keep a fraction of the data, let's say maybe 30%, that's going to be used to test the accuracy of the model to data that have not been used to parameterize the value of the parameters. So those data are not used to fix the values of theta 1, theta naught, etc. But also data that have not been used to parameterize the values of the parameters, so of the hyperparameter. So you want to keep a fraction of the data that is truly unknown to the model, that were not used to find the values of theta, that also were not used to find the values of lambda, to find the degree of complexity of the model. So this is going to be the data from the test set that is going to be like some true unknown data, some data that the model has never seen before, and some data that can be used to truly assess how well is the model going to be doing, like what kind of accuracy the model will have when you will start to use it to make some new prediction for data that were not included in the training set. Of course, here you don't necessarily have to have a separate training set, a separate validation set, and a separate test set. You can also use k-fold cross-validation as a way to try different validation set, different test set, etc. So it's going to be very similar to a linear regression model. And then if you want to see how well your model is doing, like if it's working or not in classifying the data based on their label, then you can compute a certain number of metrics. For example, a very useful metric is the classification accuracy. It's telling you how accurate is your model at classifying the data based on being class 0 or class 1. And the classification accuracy in this case is the way you can calculate it is to calculate the number of properly classified data points divided by the total number of observation, the total number of observation that you have in your data set. So you look at what is the fraction of the data that are properly classified divided by the total number of data that you have. That's the classification accuracy. So that being said, the classification accuracy is not necessarily always the best choice. There is some cases where the data, where the classes are very skewed, that it's not a good idea to just use the classification accuracy. So for example, an example where it would probably not be a good idea to only rely on the classification accuracy is when you have very unbalanced classes. For example, if your goal is to have a model that can predict whether a bridge is going to collapse or not, hopefully you have a very tiny fraction of the bridges that are going to collapse, which means that maybe in your data sets only 0.1% of the bridges are going to collapse. So those are going to a very small fraction that are actually collapsing, and all the rest, like the 99.9% of the bridges, are not collapsing. And the reason in this case why using the classification accuracy would not be a good choice is because if you have a model that can just predict that your model is always predict that it's never collapsing. Like, it's just very simple model. It's just saying, like, yeah, whatever is the value of the features, it's not gonna collapse. So it's always predicting for all the bridges, whatever the value of the features, it always say not collapsing. Then if you calculate the classification accuracy, in this case, the properly classified points is still going to be very high. In this case, if you just say that everything is not collapsing, for all those bridges, they're going to be properly classified. So you will have 99.9% of the time you will properly classified, and only 0.1% of the time you will make the wrong classification. So in this case, if you have 100 bridges, 99.1% of the time you will make the right choice, and it means that in this case your accuracy will be 0.999. So it's going to be a very, very high accuracy, but clearly your model is not good because it's doing something pretty stupid, which is to say that it's never collapsing, like the bridge is never going to collapse, but you still get a very high accuracy. So one way to avoid this is to use another type of classification metric, which is by first looking at the confusion matrix. The confusion matrix is a way to summarize how good your model is, not just at the overall accuracy, but at really predicting which points are properly classified and which one are not. So this confusion matrix is going to be like a matrix like this, where you have two boxes like this. First, on the columns will be, let's assume that you have two classes, the class 0 and the class 1. On the first two columns, you will put the data that are truly 1, or another way is to say that those are the actual class 1 data points. And then you have the true class 0, or the actual class 0 data points. So here on those columns, you will put the points based on their true value of the label, if it's truly 1 or truly 0. And then you will have on the lines of this confusion matrix, you will have the class that is actually predicted by the model. So you will put on the line the point that are predicted to be class 1 by the model, and you will put the point that are predicted to be class 0 by your model. And then based on this matrix, you will put the number of data points that you have based on for different points, based on whether they are truly 1 or truly 0, you will put them into the first column or the second column, and based on whether they are actually predicted to be 1 or predicted to be 0, you will either put them on line 1 or line 0. And at the end, so you will put the number of examples that you have in each of those four boxes. So for example, if you have a point that is truly 1, it's an actual class 1, and your model is predicted that indeed it's 1, then that's what we call a true positive. That's the model is properly predicting the class of this point. That's a positive point. It's a class 1. So class 1 is going to be, that's what we call positive. In this case, the model is predicting that it's positive, for example, positive to a given thickness, and indeed it is a true positive. So in this case, you will put the number of points that are the true positive, the point that are truly 1, truly positive, and that are indeed predicted to be positive by the model. And then the class 0 would be the negative, when you are not negative, when you are not sick, for example. So in the case, if you have some points that are actually truly 0, truly negative, if the model is indeed predicting that it's 0, then you are going to put in this box the number of points that are true negative. So when you are properly predicting the points that are actually negative, you are indeed predicting them to be negative. So those points are the points that are properly classified. But then you will have necessarily a few points that are not properly classified. So you will have certain points that are actually positives, actually 1, but your model will predict them to be negative, will predict them to be 0. So that's going to be some false negative, some point that should be positive, but they are predicted by your model to be negative. They are falsely predicted to be negative. So there are some false negative. So you will put in this box the number of false negative points, the number of points like 1, 2, 3, the number of points that are predicted to be negative, although they are actually positive. And then the last option is that you have some points that are actually negative, actually class 0, but the model is still predicting them to be positive. So that's an example where, for example, you are not sick and you do a test and the test is predicting that you are sick. So it's predicting that you are positive to this sickness, but actually you are not sick. That's an example of a false positive, where your model is predicting you to be positive, but actually you are not positive. So that's an example of false positive. And ideally, your model should have as much true positive as possible, as much true negative as possible, but as few false positive and as few false negative as possible. So then there is two useful features, two useful metrics that you can use. The first one is it's called the precision P. The precision P is every time you predict something to be positive, what is the fraction of the time that you are actually right? Every time that you are predicting that a patient is positive, how many times is the patient actually positive to this sickness? Because, for example, if you just say that nobody is positive, then like you will never have any false negative, because you will never every time if you're predicting that everybody is negative, then you will never have any false positive, because you are never predicting that the patient is actually positive. So you will never wrongly predict somebody to be positive. So that would be a bias of the model. Like you could have a test that is just predicting that nobody is sick, and you would have maybe a very high accuracy for your test, because very few people are actually sick, but it would have a very low fraction of false positive, but that would not necessarily be a good thing either. So the first aspect of the model that you want to make sure is high is your precision. Is every time you are predicting somebody to be positive, how many are actually positive? And so when you want to maximize your precision, is that you don't want to predict too many people to be positive, even though they are not positive. You want to have a high precision. You want, whenever you're predicting that somebody is positive, then it means that it's actually a positive person. You are not, for example, if you predict that everybody is positive, then most likely you will be wrong a lot of time. You will have a low prediction. So the way you calculate the prediction is that you look at among the times that you are actually predicting the patient to be positive, among the predicted ones, how many times are you actually right? So among those predicted one, how many times were you right? How many true positives were there? So if you take the ratio of the true positive divided by the predicted positive, then it gives you the precision. It gives you, whenever you predict to be positive, how many, what's the fraction of the time that you were actually right. So that's the precision. That's the first important metric, and you want the precision to be as high as possible. But again, precision is not necessarily the only thing, because if you are never predicted if you are never predicted that anybody is sick, if you are always predicting that everybody is not sick, then your precision would be 100%, because you are never making any false positive, because you are never predicted anyone to be positive. So then another other metrics that you can use that's going to also be useful is the recall. The recall is slightly different. So the recall R is this time you want to see among the points that are actual positive, among the patients that are actually positive to this sickness, how many times do you actually predict them to be positive? So every time you have some patients that are actually sick, how many times do you properly predict that they are indeed sick? And that's an important thing, because if somebody is not sick and you predict that this person is sick, then maybe it's not a big deal. Like you will just tell them that they are sick, although they are not sick. That's bad news, but it's actually not the end of the world, because at the end of the day, they are not sick. On the other hand, it's a much better deal if there is somebody who is sick and you're predicting that this person is not sick, because then this person is going to think he is not sick, and that's going to be a pretty big issue if this person doesn't get treated. So in this case, that's what is captured by the recall. You are looking at among the people or among the cases that are truly positive. So among the number of cases that are actual one, about the true one, you want to look at how many times, like among all those cases that are truly one, you want to see how many times do you properly predict them to be positive. So in this case, you will take the ratio of this divided by this. You will take the ratio of the number of true positive divided by the true one. So in the case of the precision, you take the ratio of the true positive divided by the ensemble of the predicted one. So another way to write this is that for the precision, another formula for the precision would be that it's the number of true positive. So the number of times you are properly predicting a given patient that is actually sick, you are predicting that this person is sick, divided, so the true positive divided by, so the total number of predicted one, the total number that you are predicting to be sick, so which is going to be the sum of the true positive plus the false positive. So that's going to be another expression for the precision. It's the ratio of the true positive divided by the true positive again, plus the false, the number of false positive. So you take the sum of the true positive plus the false positive, and that gives you the precision. Again, the precision is among the people that are predicted by your model to be sick, or the predicted class 1, how many are actually class 1, how many patients are actually sick. And then you have the recall. The recall, you can write it as the ratio of the true positive. So that's the people that you are predicting to be sick and that are actually sick, divided by the true positive again, but this time plus the number of false negative. And in this case, the recall, the ratio of the true positive divided by true positive plus false negative, tells you every time that you have a patient that is truly positive, that is truly sick, how many times do you actually flag this person, this patient, as being actually sick? How many times, whenever you have an example that is truly class 1, how many times do you label this example as being class 1? So typically, if your model is good, you should have at the same time a high precision and a high recall, because it's very easy to have a model that has a very high precision but a very low recall, or very low recall and a very low precision. So for example, if you are predicting that everybody is sick, whatever the test is telling you, you're predicting that everybody is sick, then it means that you will have a very high recall, because among the people who are actually sick, your model will always find those people to be actually sick. So you will never have a person that is actually sick that your model will not predicting to be sick. So you will have a very high recall, but you will have a very low precision, because among the predicted the person that are predicted to be sick by your model, maybe a lot of them will not be sick. So you will have a pretty low precision. On the other hand, if you have a model that is predicting that nobody is sick, then the precision will be very high, because you will never predicting somebody to be sick, although it is not sick, but your recall will be very low, because if you are predicting that nobody is sick, then among the people who are actually sick, then none of them would be predicted to be sick. So your fraction of true positive would be very low, your recall would be very low. So it's very easy to have a model that has a precision of 100% or a recall of 100%. What you want is to have a model that can have a good balance between precision and recall. A model that can predict it whenever somebody is sick, you want to as much as possible predict that indeed this person is sick. You want your model to be predicting that this person is sick when this person is actually sick, but you also want not to predict that everybody is sick. So you want to have a model that whenever somebody is not sick, that it's not gonna predict this person is sick too often. So you need to have a high precision and a high recall at the same time to have a good model. And one way to find the right balance between precision and recall is to calculate the F1 score, which is a formula that depends at the same time on the precision and on the recall. And the formula of the F1 score is 2 times the precision times the recall divided by precision plus recall, divided by precision plus recall. So you see that in this case, in the case of the F1 score, it's a good metric, because if the precision is very high but the recall is 0, then your F1 score would be 0 as well, if the recall is 0. On the other hand, if the recall is very high but the precision is close to 0, then your F1 score is also going to be equal to 0. So for the F1 score to be as high as possible, you need to have a good balance between a pretty high recall and a pretty high precision at the same time. So this F1 score offers a good metric to ensure that your model is indeed properly classifying the data points, that it's not always predicting everything to be positive or everything to be negative, but have a pretty good model that is making a good job with a high precision but also a high recall. So that's the main idea of logistic regression. So of course, just like in the case of regression, there is some more complex algorithm for classification problem. But logistic regression is typically working pretty well already, especially if you are creating some new features. In the same way that linear regression, when you predict when you do some of the right feature engineering, when you add the right features, linear regression can become pretty good. Here it's the same idea. Like if you use the right features, if you create the right feature by some smart feature engineering, then logistic regression can be a very powerful model to make some classification, to make some prediction about the classes of different observation based on the values of the features.